So now there are lots of other variations of this MG1, right. We saw with first, this is basically first in first out, right, FCFS. We have never seen any other discipline, but there are results for things like processor sharing, right. Remember we did GPS in Arsen. Is it GPS? Yeah, too many GPSs. Okay, so processor sharing is another sharing discipline, right, or basically round robin with very small time quantums. So that also you can emulate. So you can actually get results for MG1 with processor sharing. You can do MG1 with last come first served, right. There are several such variations which we will not get into. If you ever come across those, you can simply look at those results, right, and then try to derive them. So you have MG1 with other disciplines, other scheduling algorithms. Not all algorithms will let you get such closed form results, but you do get. So those, some of those results are summarized in Raj Jain's book. PS for example, right, is summarized. Example is processor sharing. So our round robin that we use is like an MD1, right. If you look at it, round robin is basically deterministic. But if your time quantum becomes very negligibly small, then what happens is you never finish every packet. You have to go on serving the packet multiple times. That is the difference between MD1 and with processor sharing and with round robin. Round robin, you take a packet, you technically finish it. It goes back to the queue, but that can be modeled as a queue network and so on. Whereas in processor sharing, you serve bit by bit or write microsecond by microsecond. So that packet will always be in the queue for last come first served. These are there. Okay. Then you have results for GM1, where the arrival is based on some general distribution, but the service time is Markovian, which again I am not going to go into. Then there is one special case of this MM system called the MM infinity system. Okay. So MM infinity means that whenever a customer arrives, there is always a server waiting for that, right. So this is a special, it is basically a fixed delay center, right, because a customer comes in, what is this waiting time? Always 0, you always will get a server. What is your response time? 1 by mu, right. Therefore, in some of these queuing networks, when you had a model system as a collection of queues, you simply use the MM infinity to what is called as a delay center, to model a so called delay center, which means there is always a fixed amount of delay. The delay, there is no queuing delay in the system, right, there is no queuing, there is always a server available. So in some cases we use that to model it as an MM infinity system. In fact, if you look at this MM infinity system, again maybe quiz final exam, right, you can show that the number of customers in the system at any point in time, right, is Poisson, is a Poisson distribution, right. So that Pn will be a probability for n will be a Poisson distribution, right. So that is not, that is for generally true for Mg infinity, not just MM infinity. And then you have right Gg, M, Gg1, etc. So if you look at a Gg1 system, there are some bounds in terms of the waiting time. It is not, you do not have closed form solutions, but there are at least some decent bounds that tell you that the delay will be less than this. So for example, for Gg1, the waiting time EFW is bounded by, right, so if you know the standard deviation of the arrival process, right, of the arrival inter-arrival times and the standard deviation of the inter-departure times or the inter-service times, then you can say this is an upper, sorry, what is this? Yeah, it is an upper bound on the delay. Right. Anyway, the derivation is there. If anybody wants some of these Mg1 and all its variants are in our data networks, right, this book. And if the chapters, this is all section 3.5. There are lots of other results, right? Reservation with the exhaustive, gated, polling, all those things are there, right? Which that's more useful if you go to a networks only course where you want to look at reservation also, right. So I have a reservation based access protocol where there is a reservation phase, units make the customers request for some certain number of slots, then there is a reservation, then the actual data transmission phase, right. So what is the delay in such a system compared to say TDM or Aloha and things like that. Okay, so the next assignment that you will see soon will be related to simulation of some of these basic queuing systems. We have seen the theory now, right. So I'll depending on time will present one discrete event simulation package, that is, so that will come up after I do my queuing networks work, or maybe in between I'll try to talk about that. So that way we will actually try to implement some of these queues and then vary these various parameters. We can do a lot more variations in the case of simulation based systems. For example, arrival rates, I can change that, I can set each arrival rate to whatever I want to, and then I can do per queue, right, arrival rates. Here usually we assume that all arrival rates are the same and there are multiple queues and so on. Okay, so now we are I think pretty much done with the systems. We started off with the random processes, variables, Markov chains, and finally ended up with where how come Markov chains can help in queuing systems, and we actually went to MG1 where there is no real Markov chain at all, right. We could have done MM1 without this Markov business, but anyway I think that's a useful tool to know. So we know how to handle single queue more or less, right, but the real systems, life systems are never just a single queue. It's always a connection of queues, packets flowing from one queue to another queue and then finally leaving the system, like simple transaction processing for example, right. If you want to do an online transaction with a bank, then you will be put into one queue where there is one system that is taking care of your request, then you go into another queue that will try to access the account, there is a queue that's involved, right, because there will be several requests for the account information queue. Then there will be another system that is validating, verifying and so on. So you go to authentication, getting the account, then doing the actual transaction. So you have a series of such queues that every packet essentially has to, or every transaction request has to go through. So that is our next topic, right. So there are two kinds of networks of queues. One is so called open network, other is called a closed network. So we will try to look at both. Okay. So from this point onwards I am getting into our Raj Jain's book. So this is done, we are going to Raj Jain now. Okay. And Raj Jain we are going to look at 33, 34 and so on. Okay. So this is actually chapter 32 gives you introduction. So we will start with 31 is all these queuing results, right. So 32 is what we now get started with. Queuing networks or networks of queues. Okay. So the first classification is an open network. So some definitions and then we will go to some derivations later. So this is system where there are arrivals and departures. You might wonder why we are saying the arrivals and departures, but look at the closed system where there is technically no departure, right. You are stuck. Once you enter the system you are forever going between queues. In this case there is an explicit arrival, there will be an in and an out, right, for the queuing network. And the arrival rate, it does not depend upon the system load. So the arrival process is independent of the system load. So which we in the other case the quiz that we saw, the discouraged arrival rate was there, which means that it depends upon the system load and number of customers. So in this case assume that it does not depend upon, it is just an independent set of arrivals that keep coming in at some with them, right. And we will also again for the sake of right, convenience assume that these are Poisson arrivals with rate lambda. And the servers we classify them into three types. One is called a fixed capacity server. Okay, so this is basically a single server with exponential time. Single server with exponential service time. Or we also call those as load dependent. There is another category called load dependent servers. So load dependent server means as the number of customers increases, the service capacity of the system increases, which is basically our MM1 said in a different way. If there is only one customer, the service rate is mu, right? When there are two customers, service rate is 2 mu, 3 mu and so on up to mu, right? So that's basically categorizing, and that's why it's called load dependent. As the number of customers it increases, technically there are all these the servers available, but the effective service capacity is not constant. It varies up and down with the number of customers being serviced. That's why it's called load dependent. Load dependent is harder, so we won't really look at that. And then our so called delay centers, right? This is a queue in the system which has basically theoretically infinite servers, but practically it is simply a delay center. That's all. You go in and out, there is a constant amount of time that you will spend at each or the service time. The 1 hour mu will be the average service time that you spend at each of these servers. There is no queuing in any of these places. Okay. So the network will have a whole bunch of interconnected queues, right? This system we kind of have seen before. So there is a CPU, 2 disks, and then there are certain number of jobs lined up each of these disks, including the CPU, right? This is our classical computer system model. That's why the course is called performance evaluation of computer systems. This is where we started, right? What we really are trying to look at. And what else is missing? So I have a CPU queue, jobs arrive from outside, right? Then they can go to one of these two. Okay, something has shut off, we do not know what that is. Mic still seems to work, everything is okay. Then what are the two missing lines? Usually we put, right, we like to assume that a CPU job on the CPU takes multiple iterations or multiple quantums of service before it can finally leave, right? So therefore that is that line, or it's possible that you finish the CPU service and depart. So in the quiz what we saw is there is same thing, but there is no queue there. There is only the state of a process going through, either getting serviced at the CPU or waiting for getting serviced at the disk A, disk B and so on. Okay. So that is an example of an open queue. So why is it open? Customers come in, they get serviced, and there are these loops that make you go back and forth right through this, and then you finally leave the system. So that is a typical system. So these are all the various processing stages that you go through, and you might visit DA 7 times, 8 times. That really depends upon the nature of your each job that is running on the CPU. Right? Sometimes you are disk intensive, sometimes you are only CPU intensive. Right? So all the CPU bound, IO bound, all that stuff comes in. So this is an example of an open network. So the question is, how do we solve this? How do we determine the throughput, response time, all those things in such a network? And the simplest open network is simply a tandem of queues, right, where you go from one server to another server, you arrive at rate lambda, you go to another server, spend time there, but there is no feedback in the system as such. Right. Sometimes when you go for getting permission to travel abroad, right? You go to the HOD, it's in the HOD's file, then it goes to Dean AR, and the Dean AR file, then they will forward that to Dean Financial saying pay this person, then it goes to the Dean Finance queue, right? So there you are not really going back and forth. Sometimes you will, but predominantly you don't, right? It just is a linear paperwork that gets you at the end, so you are done, right? So for such a system, right, again can we find some closed form solutions? So that is the examples of open system. Then the next is our closed queue. Where your system has a set of circulating jobs. Okay. So the jobs are permanently, technically they are not permanently in a loop, but this is, for example, we look at a system with multi-programming. Okay. So let us see with multi-programming what happens. So we again have the CPU queue, right? There are some jobs waiting here. You can go to either one of these two queues. I also need to specify the transition probabilities, right? What's the probability this job will go to, like we saw in our Markov chain, right? That we will come to later on. So this is one disk, another disk, and after their disk service, they always come back to the CPU, and then there is yeah, that's pretty much it, right? You come, so this is, so from the CPU, then you come back to the CPU and so on, right? But what we have to designate is we have to designate a couple of lines in this closed network as in and out. So basically in this case, what is it we are trying to find out? We are trying to find out, we know some properties, how long it will take, how long will you spend in this DA, how many times will you go to each disk, right? Will the process take 10 disk accesses or 20 disk accesses, and how much time does each disk access take? With all of that, then this the throughput is defined as the rate number of jobs flowing on this link from out to in, what is the number of jobs that are entering, okay? So and the assumption is that multi-programming, if one job finishes, right, there is always another job to replace it. Assume that you are always having a steady set of jobs to enter the system. So as soon as one job finishes, the next job basically replaces the old one. That's all. That's why you are technically it looks like a closed system, right? Any finishing job that leaves the CPU is replaced by another new job that is waiting to be run in the system. Okay. So now what is special here? So in the case of multi-programming, we know that I can have say only 4 jobs. Let's say only one job is running in this entire system, right? What will happen? It comes to CPU, goes to disk, right? Runs n number of times, but there is no queuing delay at all, right? So therefore delay is simply the waiting time, the service time at each of those centers. Then you add in one more job. Even then you might not see any queuing delay, because when one job is on the CPU, another job is on the disk. That's the idea of multi-programming, right? When the CPU is idle, let some other job run on the CPU. So then your utilization will slightly be more. Then as you keep on increasing n, what happens is that slowly these queues start filling up, right? Then the queuing delay starts dominating your performance, right? So if I put 50 jobs, what will happen is all these will sitting here in these queues, right? There is only about say 5 jobs can be finished per minute, right? So your effective throughput is only the number of jobs finishing per unit time, right? That is because each job goes through several of these queues, and finally it finishes after say 7 visits to disk A, 7 visits to disk B, right? And then so the required CPU intervals, it finishes. So we look at the effective throughput of the system. What is the system where my delay, right, is going to be bounded? So initially throughput will increase up to some point, then after that point your throughput will either steady or actually start coming down, right? When you start talking about thrashing and so on, when the more jobs in the system, then you are simply waiting at these queues for service, right? So no job effectively finishes, so it takes a long time for every job to finish, in which case your throughput of the system starts going down, right? Instead of 5 jobs per second, you will have only like say 1 job per second, because you are all sitting just waiting for service. So that, what is the sweet I guess what is the optimal point in terms of the number of jobs that can be in the system, right? That is what we try to find out with this kind of closed queuing network analysis, right? So that is we look at some mean solutions for that as to how we can do that, right. That is where the closed queue systems come. So that understood, right. So there is always some new job to replace an old job, that is the basic idea here, right. And what is the effective number of job completions per unit time, that is what we are interested in. From a user's perspective, it is not like your job is stuck forever, it just that from systems perspective there is always a job, right, that replaces another job. It is like our IIT system, right, students leave, but then we always have your hostel rooms filled up, right. So there is a permanent perpetual occupation of the hostel rooms. So technically we can treat all the 4th years as first year students, or next year first year students, right, or the next batch of incoming first year students. So usually we will fix n for given n, what is the throughput. So you will say given n number of users as an input, what is the throughput of the system. I put in 1000 customers, right, in the system, will I only see 5 customers finishing per unit time. So what is the optimal, if let us say I put only 1 customer, I will have 1 customer finishing per unit time, I put 2, I get 2, right. So this keeps on increasing. When I go up to say 6 customers, I can have 6 customers finishing per unit time, but when I go to 10 customers, I come back to either 6 or say 7 or something like that, in which case I am no longer optimal, right. I am having more customers, so what happens, the queuing delay simply increase beyond a point. So that is what we want to find out, this optimal n for operation of a given system. How many jobs should I keep circulating in the system such that optimal throughput is achieved, and the queuing delay is basically minimized, right. So there is some point beyond which the queues start building up, what is the value of n, I should not operate at that level. Otherwise what happens is that every job's response time, total response time will be very large, right. If I put in 20 jobs in the system, let us say you take our computer center, right, you submit jobs for running, for that will take some several hours together, everybody submits jobs, they have to limit the number of jobs that are currently running on the system, right. That is why it is a batch system, where you take in batches of jobs at a time, but what is this optimal n, you do not know. So you try to measure that based on some long time statistics, how long does each job take, how long does how many accesses that each job require on average, based on that you try to optimize your multi-programming level, right. That is one example. In the case of computer system, that is a
queue we will consider. We can consider them 3 different queues, or
these are 3 separate queues. So what we would like to do is, what is the effective number of packets or number of jobs, right, that are technically traversing this out link going into the in link, that is defined as my throughput of the system. So how do I find that out, right, given that each CPU I am spending say 2 milliseconds here, and the disk I spend say 60 milliseconds, right, on this disk I spend 80 milliseconds, right. So the job could be writing some data to disk A, then it will write a disk B for some of the application and so on. So given this kind of requirements, right, what is the effective number of jobs per second that I can sustain in the system. Okay. So here there is there is technically that self loop of going back to the ready queue is not here, it is as if that I go here, I do these things, I keep repeating like this, then I finally leave the system, right. That extra, we could have an extra loop also, but that is not the outline. You have to define one of these lines as the out to in line, and then say on this line what is the rate of jobs that I am seeing, right. Only when a job, right, so if I have another extra line here which is simply bringing back to the CPU queue itself, I define this as the line where I would exit the system. When a job finishes, it is basically traversing the outline. So what is this from here to here is because this is my replacement rate, right. Depending on the number of jobs I finish, I will be able to replenish, right. So what is that rate, that is what we are trying to get to, that we will see when we get to the closed queue analysis, then we will get a better grasp of it, and we will also implement these things, what the heck, right. Once you get your basic single queue done, networks of queues is very simple in a simulator, right, then we can run it and then see what we are getting. Other questions before we start looking at closed form solutions for these queues. Okay, so let us look at our first the tandem queue, right, and see how we can derive the probability of occupation. Oh, and I will come back to that later. So this I can also have hybrid queues where some part of the system is closed, some part of it is open, right. Let us not confuse ourselves right now, we will just leave this open and closed. So let us look at tandem queue. Okay, so now we will look at the simple tandem queues of MM1 queues, right. So there is a series of MM1 queues, each of them having this service rate. So customer or packet arrives, gets serviced at the first queue with rate mu1, second mu2 and so on, right, and there is no other external input to the system. Only entry point is that lambda at the first queue, no cross queues. Okay. So to analyze this, and so basically we want to find out the probability that there are n1 customers in Q1, n2 in Q2, n3 in Q3 and so on. That is, once we get that, then I can derive the expected number of customers in the system and all my response time, everything I can derive. Okay. So the first thing that people had to figure out is what is the output process of a MM1 queue. What is the, right, packets are departing the queue, what is that process? Because that process is the input to the second queue, right. So what is the departure process of a MM1 queue? Of course this queue has to be stable, right, so otherwise not that interesting. Okay. So what could this process be? MM1. Also Poisson with rate mu1. See, I am only generating my mu1 is say 1000 million packets per second. Only 10 packets per second are entering the queue. Will my departure process be a Poisson process with rate 10,000 or 1 million packets per second? Simply random. Right? So your input equals to your this under steady state, number of customers entering equals number of customers leaving per unit time, and it so happens that it can be shown to be a Poisson process with rate lambda. Okay. So this is what is called as Burke's theorem. So this is a classic result. I think this person was also at AT&T. A lot of these results, queuing theory results, came from those AT&T folks, because AT&T labs right, is very keen on cutting down delays and so on, right, the telephone network. So this is one of the early results. Okay. So shall we try to prove this? So how do we prove that? So we look at two cases, right. One, when the queue is never empty. If the queue is always full, right, what will be the departure rate? If the queue is always full, right, the queue is never empty, what will be the departure rate? What will be the inter-departure time, service time, or inter-departure time distribution? Okay, let us do this one at a time. Okay, 1. As long as the queue is non-empty. So I am looking at the departure process. So I want to know the inter-departure time distribution, right. So inter-departure time distribution will be what? In other words, the time between two customers departing. So the queue is always having somebody to serve, right? What will that be? 1 by service time. It is simply exponential with rate mu. Now it is exponential with rate mu. Okay. When the queue is always full, right, what is each customer comes, gets serviced, what is the time? 1 over mu, right. The service time is exponential with service with rate mu. So between successive customers departing the system, the distribution will simply be exponential with rate mu. Okay.
Minimum of all those mu's.
No, this is just the process. This is just the process. Oh, sorry, no, only one queue. I'm not. Oh yeah, we are not yet going to. Forget the tandem. Ah, no, let's not. before I go to my tandem, right, I need to first of all, I am looking at the system at this point here, right. We are just looking at a single M1 queue, right, 1 mm1 queue. To solve this I need to know this result first, then I can solve the second ones after that. Okay. So what is the process coming out of the first queue, because I need to know the input process for the second queue. I do not know that, right. I am stating that it is Poisson. If I know it is Poisson, then I can solve all of these independently, but I need to first of all prove that it is Poisson. Okay. Okay. So this, if the queue is not empty, interdeparture time distribution is exponential with rate mu. Okay. Now let us look at the scenario where one customer has just now left, right. The last customer in the queue has been serviced, therefore that guy has left. Now we need to find out the next departure. So one depart, that is the last departure has happened, we are waiting for the next departure to take place, right. So when will the next departure happen? So right now the queue is empty. Okay. So we will write this, if departure, the queue empties. So you will have to wait for two things, right. What is that? Wait for the next arrival, right. So what is the time for the next arrival? That is exponential So the inter-arrival times is exponential and it is memoryless, right. So whatever point in time I say what is the arrival distribution, it is always this inter-arrival with exponential with rate lambda, right. Okay. So wait for the next arrival, right, which takes, we will just say that exponential lambda. Okay. Then, so for this arrival to come I have to wait for exp of lambda, right. Then for this arrival to leave, so this come to empty queue, therefore it will get serviced already, right. So therefore the time to next departure, right. So I will also wait for the this. It is Poisson with yes, Poisson, but the inter arrival is exponential. I am looking at the inter arrival time. So Poisson process, arrival process, the inter arrival time is exponential with rate same lambda. Wait for this arrival to get serviced and depart, right. And what is that? Right. Right. So when the queue is empty, you have to wait for one arrival, then that arrival has to depart, right. So what do I have now? So what is this A and B combined define? It is a hypo exponential, right. There are two exponential processes back to back, there is no queuing at all, right. There is one of length, one of rate lambda, one of rate mu, right. For therefore what is the so what is the mean now? The total response time, the total waiting time for the next departure. Now this is my inter departure time, right. Inter departure time when the queue is always full is exponential with rate mu. When the queue just got empty, it is hypo exponential with this lambda plus lambda mu combination, right. So now let us do that, right. So therefore the inter departure is hypo exponential with the parameters, the first is lambda, second is mu. Okay. So now what is the probability that So there are two cases now, one is exponential mu, one is hyper exponential with lambda and mu. So what is the probability that you will encounter exponential mu? Rho, right? Rho is the probability, the utilization, probability the queue is always occupied. 1 minus rho is P naught, probability that the system is going to be empty, right? So therefore effective interdeparture distribution is simply probability of queue being empty into this f of right. So the interdeparture time CDF, we will call that FD of t, is given by rho into 1 minus okay. So this is the first part, right, 1 minus e power minus mu t. Then this is 1 minus mu into this we will have to go back and right. So 1 minus lambda 1 divided by, or 1 minus lambda 2 by lambda 1 plus lambda 2 e power minus lambda 1 of t and so on, right. We can go back and refer that. So that is 1 minus yeah mu lambda 2 minus lambda t plus lambda by mu minus lambda e power minus mu t. This is the FD of t, right, the CDF of the hyper exponential. And this I have not done the computation, but we can do that later, and then I have not actually done the worked out, but apparently it works out to 1 minus e power minus lambda t. So before next class verify this because of the fact that rho is there, right. So rho is lambda by mu. So I have not checked this, I just found this proof on the web and I said, oh well, this should be correct, but looking at it I am kind of now even worried whether this is going to work out or not because there is 1 minus mu that is there, okay, and then okay, I guess we can make mu by minus 1 minus yeah, I can take out the mu there and make it 1 minus rho, and here also, okay, well we will check it out, okay. So this is your FD of t, 1 minus e power minus lambda t, and that is basically your arrival process, right. If A of t is the arrival process, inter-arrival process CDF, therefore your departures are also Poisson with rate lambda. So this result is known, this particular derivation I have to check, okay. So now I know that whatever the process, departure process from the first queue is also Poisson with rate lambda, it goes to the second queue, right. So now I can analyze all these queues independently, right. So what is the total time spent is the time spent in the first queue plus time spent in the second queue. So these queues are basically now going to be independent, okay. Again, some of the proof we are just sort of stating as is, but we can check, we will a couple of minutes or so, right. So the queues can be, so that result is what led to this analysis, that they can be analyzed independently of each other. Okay. So if I define rho I is lambda by mu I, right, the probability of Ni jobs in Qi is the same thing, rho to the n into 1 minus rho. So it is 1 minus rho I and we will assume that this is less than 1. Okay. And then if you look at the joint probability, that there are the joint probability of queue length. Queue length basically the number of customers, not just the length, right, including okay, that is basically what is the probability that there are n1 customers in the first queue, n2 customers in the second queue, and nm customers in the third queue. Okay, that is simply 1 minus simply the product of all the PMs, number of customers, right, because they are all independent of each other. So when there are 10 customers in Q1, does not matter, there may be 20 customers, right, the probability of having 10 and 20 is independent in each of those queues. If there is dependence, then it becomes a problem, right, that is why this MM1 assumption is useful, that we can show that they are dependent of each other, and therefore the joint distribution of having so many customers in each of these queues is simply the product of all the. So this is what is this? This is the number of customers having n1 customers in Q1 into n1 n2 customers in Q2 and so on. So this is simply a product, right. So this is what is called as in queuing network results, this is called a product form distribution, right. So this is called a product form network. So whenever I have a network which has this product form nature, I can analyze the queues independent of each other.
In such case, you have the end-to-end delay as a summation of the
Summation all this, yeah, summation of all the delays. Yeah. So where we see a tandem queue such as this is where you have a say MPLS path, right. Only thing is there is some cross traffic also coming in, there is extra lambdas that feed in, right, but in this case and because you are sharing the link, right, here is a link being shared among. So if you can somehow abstract it away, right, if you are doing for example congestion control analysis, you are going through several queues, right, TCP for example goes through several queues, you want to find out the end-to-end delay. Some more approximations have to be done, but this is usually some sort of starting point for things like go back and select repeat and so on. We can use this as one for initial setup. Okay, so we will do one small example and then we will stop. Okay. So let us look at a 2 queue system. Right, so 2 MM1 is in tandem. So what is the probability, or what is the E of n, right? What is E of n? E of n is the total number of customers in the system, right? Total number of customers in the entire this tandem queue system. What is that going to be? From basic we did E of n1, we said what, right? So this is basically what is there are n1 customers in the first queue, n2 customers in the second queue, then n1 plus n2, right, into the probability that there are, right, for every n1 what is the, right, given what is the value of n2 for some value of n2, n1 plus n2 into probability of n1 plus. We did npn, right, for the basic case. So this is simply n1 plus n2 p of n1. And what is that? Now I know that this is product form, right, this is a product form solution, therefore I can replace that with this is 1 minus rho 1 n1 rho 2 n2. So how do you solve this further? So what will you get at the end of it? E of n1 plus E of n2, right? So that I will let you work it out, right? So first case, make n1 as a constant, right? Sum over n2, and then keep n1 constant. You will find out that you will end up with something. Then sum it over the outer index n1. Then you will finally end up with E of n1 plus n2. So that's that shows us that we can simply add up all the. Right? So once I get E of n, then I know the E of r in each queue. Then to get the total delay, I simply do E of r1 plus E of r2 and so on. Right? That's all. So this after derivation should come to hope. Okay, questions? So in general, what we will see is there are some classes of networks for which this product form the network conditions apply, and that's what people have tried to do. Okay, so if I just take a single tandem, yes, it is product form. What if I have an arbitrary set of open networks, open queuing networks? Is that closed form or this product form? Then that is also product form. Or arbitrary network of closed queues, but all of them is exponential service times, right? So arbitrary network of even MMM is also okay. New networks is also closed form, right? So you say we start with this tandem is closed, is product form. Open network with MM1 queues is also product form. Open and then closed with MM1 is also product form. So these have been results that got proved in the 70s and 80s as people try to expand on where this product form can be applied. Then there is a classic paper which is 75 or so that says there are several, even for other types of disciplines, not just FCFS, even with multiple classes of traffic, you can have all of these things done. So we will sort of just go through those main results. Then we will look at actually techniques as to how to solve some of these and get the throughput values that we want.